Welcome to Tech Bytes and News, your daily roundup of articles featured in Hacker News. Today, we're diving into a fascinating exploration of medieval physics, specifically the surprisingly accurate range calculations for a trebuchet.
A trebuchet, huh? Sounds like a fun challenge. I'm ready to get technical. What's the core argument here?
The author cleverly uses energy conservation and basic kinematic principles to estimate a trebuchet's range, without getting bogged down in complex mechanical details. It's a brilliant simplification.
So, they're not doing a full-blown mechanical simulation? That's smart. How do they approach the problem then?
They start with potential energy, the energy stored in the raised counterweight. They use the formula delta E equals mg delta h, where m is the counterweight mass, g is gravity, and delta h is the height change. Ingenious!
Right, potential energy converted to kinetic energy of the projectile. But they don't calculate the exact energy transfer, right? There are losses, right?
Exactly. They assume an 80% efficiency, acknowledging energy losses due to friction and the trebuchet's mechanics. This is a realistic approach, It makes the calculation more manageable.
I see. So they get a launch velocity. Then what? How do they get the range?
This is where it gets really interesting. Instead of diving straight into calculus, they use a clever graphical approach to derive the equations of motion. They visualize the area under acceleration time and velocity time graphs to find the distance traveled.
That's a fantastic pedagogical approach. It makes the concepts much more intuitive, doesn't it? So they calculate the time of flight first, right?
Precisely. They first calculate the time of flight assuming a horizontal launch, then use that to find the horizontal range. The surprising result? The range is independent of the planet's gravity.
Wait, what? That's counterintuitive. How is that possible? I mean, gravity pulls the projectile down, right? Shouldn't stronger gravity mean a shorter range?
That's the beautiful part. The author argues that gravity affects both the launch and the fall. A stronger gravity leads to a faster launch, but also a quicker fall. These effects cancel each other out, resulting in the same range, regardless of the gravitational acceleration. Amazing!
That's mind-blowing. So they then refine the calculation for a 45-degree launch angle, which maximizes the range, right? And they use the quadratic formula to solve for the time of flight in this case?
Yes. The 45-degree launch angle is a classic optimization problem. And yes, they correctly use the quadratic formula to solve for the time of flight, which is now more complex because of the vertical component of the initial velocity. The final result is a range of around 210 meters.
And that's remarkably close to historical accounts, isn't it? Impressive.
Indeed. The author's estimations are surprisingly accurate, considering the simplifications made. It showcases the power of clever approximations and intuitive physics reasoning. This is a great example of how to approach complex problems with elegant solutions.
Absolutely. This article is a fantastic blend of historical context, insightful physics, and clear explanations. It's a great example of how to make complex topics accessible and engaging. Thanks for sharing this.
My pleasure. And that's all the time we have for today's Tech Bytes and News. Join us tomorrow for another exciting deep dive into the world of technology and science. Goodbye.
Bye-bye.